Welcome to NASA's Jet Propulsion Laboratory here in Southern California. I'm Marina Jurica, and we're coming to you live from a very special place today. This is a spacecraft assembly facility clean room here at JPL, and we're going to talk to you today a little bit about an upcoming Earth science mission. But we're in a clean room, so that's why we are all wearing protective gear in here today. Now, in this clean room, spacecraft have been put together for decades. And as I mentioned, today we're talking to you about an upcoming Earth science mission called NISAR. Now, NISAR is going to be able to measure changes in the land and on ice all across the Earth's surface with unprecedented precision. So we're going to be able to observe things like volcanoes and earthquakes as well as glaciers. Now, it's set to launch in 2024, so next year. So you might be wondering, why are we talking about NISAR now when it's launching next year? Well, this is the scientific heart of NISAR here behind me. And shortly, it is going to be leaving JPL and heading to India, where it is going to go through further testing and integration. You heard me right, India. NISAR is a joint collaboration with the Indian Space Research Organization, ISRO, and NASA, and it's actually going to be launching from southern India as well next year. So a lot of great things to look forward to. Now today we're going to educate and learn so much about NISAR with two mission members. Our first mission member will be the Deputy Project Scientist, Sue Owen, and then next we'll be talking to the Deputy Project Manager, Wendy Edelstein, and we're going to be answering your questions. So if you have any questions at all, make sure you put them in the comment box. And also we're using the hashtag AskNASA on Twitter, and we'll get to all of your questions later on in the program. So first up, we're going to talk to Sue. Thank you so much for being here today, Sue.
Thank you for inviting me, and thanks everybody for showing up.
So like I said, this is a really cool place to be in. So tell the folks at home a little bit about where we are, why today is important, and looking at the scientific heart of NISAR.
Oh, thank you. So we're here in the spacecraft assembly facility, as you mentioned. It's a clean room where the spacecraft instruments are put together and integrated. So you can see behind you the radar instruments for NISAR. So we're here today, as you mentioned, because it is about to get sent to India. And there are many people who have been involved with involved with NISAR, who are here today to commemorate this really important milestone for NISAR. So the engineers have been hard at work integrating the two radars. So NISAR stands for the NASA ISRO Synthetic Aperture Radar Mission. And so it's a radar mission that's going to be observing the Earth and making the very high precision measurements. But right now, they're finished with integrating the two different radars, the L band, which is a slightly longer wavelength, and the S band, which is a slightly shorter wavelength. And it is about to get sent off to India. And as a result, we've had people from ISRO, the ISRO chairman's here, people from NASA headquarters, the head of Earth Science for NASA has been here today. And you here get to be part of that through this social media activity.
Yes, we're bringing them here to send off NISAR with all the fanfare it deserves, for sure. So there's some key science instruments that are involved with this. Tell me a little bit about that.
Okay, so the science instruments that are here that are getting built and integrated, it's synthetic aperture radar. So what does that mean? So the synthetic aperture part is that we're using the movement of the satellite through space to simulate a very large aperture for that radar. And so what does that mean? That means that we get very good spatial coverage, so we can cover more of the land and cover a greater part of the globe, as well as getting very, what we say, high spatial resolution. So that means we can measure things that occur over smaller parts of the Earth. So we'll be able to see changes that happen over areas that are as small as 10 meters, or if we're looking, say, at how changes occurring in urban areas, we'll be able to measure changes that occur over less than a city block. Or if we're looking at changes in agricultural fields, we'll be able to see changes that occur over the scale of about 200 meters, which is about the scale of some agricultural fields, crop fields. So a lot of really exciting data that we're going to be getting from this radar. The radar is going to be basically transmitted from the satellite, bounced off the Earth, and then received by the satellite. And then we'll use that signal to, as you mentioned, look at how the Earth is changing. So what does that mean? One key measurement is using those signals to measure how fast the ground is moving. So when we're looking at volcanoes, for example, we can see if the volcano is moving upwards because there's magma coming underneath it. If we're looking at landslides, we could look at to see if landslides are starting to slip as a precursor to more catastrophic motion. If we're looking in areas where people have been pulling groundwater from underneath the surface of the Earth, we can see that that causes the ground to sink. And so that gives us an idea of how much groundwater is being pulled from the ground, as well as whether or not that sinking is affecting any of the bridge, roads, train tracks, buildings that are built on top of the surface. So lots of really exciting measurements of how the Earth's surface is going to change. That's just a few.
Right, and that's what we've always talked about, Sue. For folks at home, what I love about NISAR is it affects each and every one of you, and so that's what's amazing about it. Its applications are hundreds and hundreds of things. So tell folks at home a little bit about maybe a few of them that you're really interested in,
okay,
or that they would be really affected by, because that's what's so great about this, is it is really groundbreaking.
Yes, good pun. So I'm going to talk about two, and one I've already mentioned a little bit before, and that is volcanoes, because that's kind of near and dear to my heart. I started out as a volcano scientist, and so what we're really excited about with NISAR is by using the L-band radar. So L-band, it's a radar that can see through vegetation more than the global radar measurements that are currently up there. So there's volcanoes that we can't measure very accurately right now, or as accurately as we would like to, because we don't have the continuous repeated observations from the L-band radar. And so people will be able to monitor volcanoes, see when they are starting to be active, see once they start to be active if they are getting closer to eruptions, and that's really important. Even if you don't live next to a volcano, a lot of the global flights go over areas that have volcanic activity, and so it's really important for airline traffic to also be aware of when volcanoes are erupting, even if they're far away from where people live. Another application that's really important is how NISAR is going to be used to measure soil moisture. So we're going to be able to measure how wet the top layer of the Earth is globally at field scales, as I mentioned before. So that's going to be helpful not only for agricultural management, but also for seeing where areas are wet or dry as we're looking at where wildfires might happen. So it will help with wildfire management, and it will also be helpful in trying to understand how ecosystems are changing in response to changing soil moisture. So those are just two of many applications that NISAR has.
Yes, just two. And you can always go on to NISAR's website and see the many applications and also the many early adopters that
Yes.
are adopting NISAR's program. And so you touched on this just a little bit, Sue, but I think that folks at home will be so fascinated by this. But it sees through all weather, and we've never been able to do that before. So like clouds, rain, thunderstorms, it sees through all that.
Yes, no, that's a really good point. So one of the other exciting things about the radar data is that it can see through clouds. And so there are areas on the globe where we haven't been able to study as well as consistently as we would like, because they're mostly covered in cloud cover. Or say, if we're trying to see where there is flooding after a major hurricane or a major storm, radar can be used to map the extent of the floods, and it can see through the clouds that are often still there. So, it complements the type of data that we get from optical satellites really nicely because it is able to see through clouds.
That's great. So tell folks at home a little bit about what it is that you do on the mission as the Deputy Project Scientist.
Great. Yeah, no, Deputy Project Scientist is a really great job. I've been in it for about 3 years now. And what we do is, I work closely with a project scientist, and my job is primarily to interact with and interface with the engineers to make sure that as they're building the instrument, as we're building the science data systems, we're keeping in mind the science that's going to be done at the end and making sure that it's that any decisions that are made are going to maximize the science that we get at the end. And then the other part is talking to the science community, including the science community in India. They're part of this project as well. We have ISRO counterparts on the science team. And we're telling them about the type of data that NISAR is going to provide. It's a new type of measurement. So we're doing a lot of communicating with the science community to get them ready so that once NISAR launches and once the data starts flowing, they're ready to start doing their science.
That's so amazing. It's just putting the tools in their hands so
Yes.
they are just ready to go.
Yeah.
All right, well, we're getting tons of questions from you, so thank you so much for interacting with us. So are you ready for a couple of questions from the public?
Sure.
All right, Sue. First comes from Maddie Doser on Instagram asking, can the satellite be used to document weather patterns?
So the radar is really seeing through the weather. So what we can do is document the influence of the weather patterns on the ground. So when I was talking about flooding, so if you have storms that are causing flooding areas, that's what the radar is going to be really good at documenting. Not so much seeing where the clouds are, because we're actually, the radar just shoots right through the clouds.
All right. Next comes from Ali Braun on Instagram asking, how is NISAR different from missions like SWAT, which just launched in December?
Yeah, that's a really great question. So NASA has a lot of Earth science satellites, and sometimes at the very high level they can sound kind of similar. So SWAT has a radar as well, but it is it's specialized to be looking at how the oceans are changing. So it is going to be focused on measuring in the oceans. And NISAR is not going to be making very much observations over the ocean. SWAT is also going to be measuring the water on land, but it's going to be looking at the elevation and the change in the elevation of the water. Whereas what NISAR is going to be focused more on how the land is changing, how the ice is changing, and it will be able to detect where the boundary between the land and the water is. And so we call that the water extent. So that's what we use to say map floods and to map changes in wetlands. So it's a very complementary set of observations that SWAT is making.
And like you said, it's so complementary. A lot of our Earth satellite missions, when they are grouped together, the data becomes even more amazing than it is by itself.
Yes. No, and I like to think of it kind of like if you're going to the doctor, the doctor doesn't just take one measurement. They don't just, take a blood test and then they're able to solve all of the things that might be wrong with you or you might be having problems with. We always, when we go to the doctor, we're used to getting multiple tests so that the doctor can really figure out what's going on within you. And so the same is true for how we're making observations of the Earth. We need multiple sets of data to really diagnose how the Earth is changing and to help make sure that we can manage the Earth's response to what we're doing.
That's right, for the future.
Yes.
Yes, all right. Next is the Lord Plord on Instagram asks, that's a great name.
Yeah.
Is the data received from the satellite open to the public?
Yes, so all NASA data is free and open. The data from NISAR will be distributed through we call it a DAC, a Distributed Active Archive Center. It's the Alaska Satellite Facility up in Fairbanks, Alaska is the DAC, the official DAC for NISAR data. And so 90 days after launch, after we go through our commissioning phase, the data will be available through the ASF DAC.
That's awesome. All right. Okay. Well, that's all the questions that we have for you, Sue, but we're going to bring you back a little bit later to talk with Wendy as well. But before you go, I know you've been on the mission for a while. So tell us how long you've been on the mission and maybe a really memorable memory that you have.
Oh, wow. Okay. So I've been deputy project scientist for about 3 years, and then I've been working with the team on applications for about 10 years or so. And, for me, most recently, a really memorable memory is we had our NISAR Science Community Workshop just this past summer in Pasadena. And this was something that we had planned to do in 2020. And then it got postponed, and then it got postponed again. And then when we did meet, there was so much excitement from the science community about NISAR. And so, people were just so excited to get this data. So that was just an amazing event for me and lots of fun memories.
Well, I'm so glad that things are calming down and we're finally getting a little bit back to normal. But thank you so much for being here with us, Sue. We'll see you in just a little bit.
Great.
And if you're just joining us, We are here at Jet Propulsion Laboratory in Southern California in a clean room. That's why we're wearing protective gear. And we're talking about an upcoming Earth mission called NISAR. And now we're switching over here, gears to Wendy, who is the Deputy Project Manager. Thanks so much for joining us, Wendy.
Oh, I'm glad to be here. Hello, everybody.
So tell us a little bit about what it is that you do. What is a Deputy Project Manager?
So I would say a Deputy Project Manager, I wear a lot of hats. I'm responsible for basically making sure this beautiful instrument is designed, built, tested properly. I need to work carefully with our scientists like Sue and others to make sure that we're meeting the mission objectives and we're building the right instrument. That takes a fair amount of effort to make sure we can do that properly. I work when there's problems. I help deal with issues that they come up. I help remove roadblocks when there's a problem. So all those things I have to do. Another important part of my job, of course, is to work with our ISRO colleagues because we work across the world from them. And so it takes a lot of collaboration and coordination and a lot of late night telecons to work with them and to make sure that we understand what we're doing, we have built the right interfaces with our designs, and that ultimately the two systems will come together. So that takes sort of the third component of my job.
Yes, and time changes, global pandemics, you guys have been through it all, which has been so amazing because you have overcome.
Yeah, it has been, it's interesting because we started testing the two systems. We started testing the L-band radar, which is right behind me, in 2019 and 2020 through the pandemic. And then also through the pandemic, the S-band radar from India joined us here at JPL. That got integrated. We had many people from India who joined us from there. We worked together side by side through the pandemic, which was challenging. And now for the last year or so, we've been actually finalizing the testing of this system and putting it all together, finishing the testing and preparing to take it to India for the final phase of the journey.
So I know people at home are like, okay, let's talk about the instrument, right?
Absolutely.
I mean, this is really cool. So can you point out what exactly it is that we're looking at here? It's considered the scientific heart, which Sue talked about a little bit, but just point out some really cool things to folks at home.
Right, so this whole thing, some people might think it's the actual spacecraft. This is just the instrument. The spacecraft is not even here yet. That's going to get attached to the instrument when we move to India. But right here is what's called the radar instrument structure. What you see is all this gold is covering a lot of electronics, but the electronics are broken up into two pieces. We have the S-band system that Sue talked about. That's the part that was contributed by ISRO. That's buried inside the system. You can't see that anymore because we've integrated it, installed it, closed everything up, it's buttoned up. But you still can see, if you look carefully, is a lot of the L-band radar electronics on the outside of the system. And you can see, if you look carefully, there's some silver patches. Those are all what we call transmit-receive modules. Those are the primary interface to our antenna feed. And there's 24 of them, 12H polarization and 12V polarization. And together they make basically 24 separate radars. So it's like testing 24 different systems. But those all work together, and then those white panels across the top, there's 6 panels, those are our antenna feeds. Those are the L-band feeds, and right below it is the S-band antenna feeds. So those two radiate into the antenna, the big large reflector that is not here right now, as you can see, because we boxed that up. But that's how we would normally operate this with that large antenna out in this region where we basically use that to reflect the RF frequencies down to Earth. So right now, what you see is the radar instrument by itself without the antenna.
And it's undergone a lot of testing here. It will continue in India as well, but it's already been tested a lot at JPL as well.
Right, we've been testing since 2019, so with different phases, system level testing, and then we moved on to integrated with the L-band and S-band, so making sure the two systems work well together. And then in the last 6 months, we've been doing what we call environmental testing. What that means is we have to simulate the launch environments. Vibration, right? The launch vehicle, the rocket, is a lot of vibration, so we have to simulate that. So we do a thermal vibration test. We also do several thermal vacuum tests to simulate the space environment, and we have to done 2 of those because one of our thermal vacuum tests was with the antenna and the boom wrapped around here. It's not shown now, so that's what we call our launch environment, so we tested it there. And then in December was our last test where we had taken off the boom and reflector, and we do what's a science thermal vacuum test to really simulate what the operations on orbit will be like. So we've just finished the last of our testing in December. We're doing a sequence right now of last tests to operate more flight-like, we call the mission scenario test, and we're doing our last radar test, and we're ready to tear it down starting Monday and start getting ready to ship it to India next week.
Oh, it's going to be a bittersweet moment, I'm
It
sure,
will be,
for
yes.
everybody, yes. And we're going to get to your questions again with Wendy and with Sue here in just a moment. But before we get to that, Wendy, tell me a little bit about what sets NISAR apart from other Earth missions, and why is the data so unprecedented?
Well, so most science missions are, focused science objectives, right? They're looking at soil moisture, ocean salinity, one objective. But NISAR is unique because it really, I think Sue talked about this, it covers a wide range of science objectives. We call it something like the Swiss Army knife of science, of Earth science missions, because it does a lot. To do something like that requires a really complicated system. It has to have a lot of flexibility in terms of how much power it generates, the resolution, how stable it is to make these surface change measurements. That's probably one of the most challenging requirements, is to make sure that we can do these change requirements at the centimeter level. That requires a super stable system. So we spend a lot of time making sure this system is very stable over time, over temperature, over all environments. So that's another key thing. And then the last thing is that we have a lot of data. You heard that we are generating a lot of data for this. Enormous amounts of data. 40 something terabits of data a day. After processing, it's like 300 or 80 terabytes a day. So it's a huge volume of data that's completely unprecedented. And so it's just different than any other mission. We've never generated this much science. And then the other interesting feature of this system is the big antenna. You don't see it now, but if you've seen
It's so beautiful.
If you've ever seen any images of NISAR, you say, well, where's the antenna? Well, it's too big to have it right here deployed in this system because we have to deploy it in a special facility, but it's getting ready to launch. But that's the other unique feature, is this antenna is the largest antenna that NASA has flown for a science mission. So it's a lot of firsts for the NISAR mission.
That's great. And if you want to see what NISAR looks like, we have animations, and we'll drop those in the chat for you too as well, so that you can look them up, so that you can actually see it in its full capacity, or what it will look like once it is up and launched.
Right.
All right, so let's get to some of your questions here for Wendy. All right, first question comes from Ethan M. Weber on Instagram asking, are there any plans in place to mitigate damage to the antenna from space debris impacts?
Oh, great question. So yes, what we have is we deal with orbital debris, is what we call it, two ways. One is by design. We've designed our systems to be able to withstand any impacts from debris. We put extra layers of materials on. Actually, some of these blankets that you see here on it actually have a part of their purpose is to protect the electronics from orbital debris. The antenna is protected. We've done a lot of designs and studies and analysis to prove that very fragile looking antenna that looks like it will just fall apart, it actually can withstand debris that can fly right through it. So it's all built into the design. And then of course, so that's the design piece, but then also in terms of operations, we have ways to move the spacecraft and maneuver away, because we keep track of orbital debris, and we can move the spacecraft if we recognize that there's some debris coming our way.
And thermal blanketing too, a lot of people always ask what the gold is. So
Right.
tell us a little bit about what all the gold is.
So the gold it's interesting. The thermal design is a big part of a spacecraft, right? It's a very extreme environment. It can be very cold, it can be very hot. And as you can see, we have actually electronics that just are on the outside of the system. They're not protected by anything. So we have used thermal blankets and other thermal materials to protect the spacecraft, to keep it kind of like a cooler, right? It keeps it warm if it's cold outside, and it keeps it cool if it's hot outside. So we have some aspects of it that are that we want to keep our boxes cold. So you can see all that silver stuff on that. That's very reflective, so that keeps it nice and cool. Our boom that you can't see right now is flat because we want to keep it warm. So we actually use different materials depending on what part of the spacecraft it's on and what environment it's exposed to. So it's a big art to deal with the thermal design.
That's great. Thank you, Wendy. Next question comes from tog.scgl on Instagram asking, do you have cameras to check the antenna deployment like SWAT?
Yes, yes we do. Actually, it's being contributed by the ISRO partners. They have some cameras on board to actually watch the deployment. So that is built into our design. I worked on this MAP mission. We never had cameras. We always said that's probably a good thing from now on. So yes, there are cameras.
Very cool. And last, Galanzoga4 on Instagram asks, how much does the antenna reflector weigh, and why does it have to be so large?
So it weighs about 120 pounds for just the reflector, which is pretty lightweight. And the reason why it has to be so large, and it's 12 meters, so that's like 30 something, 40 feet across, so it's very large, and that's driven by the resolution requirements of the system. So we need high resolution, and that's driven by that antenna size.
Okay, great. We're going to bring Sue back in. Again, the Deputy Project Scientist and the Deputy Project Manager here. So for Sue, it's him on Instagram asks, what makes it different from other Earth observing satellites, which Wendy touched on, but I'm sure you can elaborate a little more.
Yeah, so
And if we want to move down a little bit here, so we can give everyone a much better view of this gorgeous satellite behind us. There we go.
Yeah. So Wendy mentioned that it is this Swiss Army knife of Earth, of Earth observing satellites, and that it does have a really broad range of science applications. So there are scientists who are studying the Earth's ecosystems, who are studying the Earth's ice sheets, who are studying the Earth's, solid Earth systems, natural hazards that are interested in that this NISAR data is going to be useful for. So I think it is unique in the range of science applications that it's going to have. And it fills in a gap in the current Earth observing set of satellites that we have on there, that we have up there. We don't have a satellite that is making these types of radar imagery, radar measurements that allow us to see the types of change. So I mentioned, it's going to be able to measure how fast the surface of the Earth is moving. And so it's going to, provide that data in a way that we don't have it, we haven't been able to measure it so far. The other really unique thing about NISAR is the amount of data. So we are going to be generating 80 terabytes of data products per day, which is way more than any other NASA Earth observing mission has collected so far, and any other Earth observing mission has collected so far. And that just gives you a hint of the content-rich nature of the data set that NISAR is going to be providing. So hopefully that tells you a little bit about how NISAR is different.
Scientists aren't going to know what to do. It's just so much. It's going to be a smorgasbord.
Well, and that's why we're talking to them now.
Yes, exactly. All right. So now we have a question from the Cooler Afid on Instagram asking, how will the reflector antenna be folded, sent up, and opened in space? So you can address that.
I'll take that one. So it actually has a boom. You don't see this here, but it has a boom that is broken into 4 segments. It wraps around the whole structure. So actually I can point to you. Over here is where the boom attaches. It wraps around. There's a joint, a hinge here. It folds over here, and then it folds and wraps around over here. So the reflector, when we launch it, is actually going to be on the far side of the spacecraft, tied down with a lot of launch restraints, very, very cozy and protected, and can withstand all the launch loads. And then we have to carefully, on orbit, then it takes several days to actually one hinge at a time. We open up the antenna, and then we open up the boom, and then once that's all deployed, then we release the reflector.
And it takes a while.
Yes.
So folks know at home, this isn't something that happens in 10 minutes. It takes a couple of days to make sure everything's going right. And
we do it very carefully. We could do it faster, but we choose not to. We
Yes.
want to do it carefully, so we do one hinge a day for over several days, and then we do the boom and reflector. So it's about a 10-day operation. What's interesting is I've seen one in person, and it only takes about 30 minutes to actually deploy the reflector, but we build in margins so that we can deal with any uncertainty or surprises along the way.
so now I think Sue can take the next one. Daniel Fisher on YouTube asks, what will the satellite tell us about global warming and climate change?
Oh, that's a really good question. So what the NISAR satellite is going to be able to do for climate change, there's a couple of things that, that just off the top of my head. One of the main things is measuring how fast the ice sheets are melting. So as the climate is warming and as the oceans are warming, we're seeing increased rate of the glaciers melting, both in the mountains and in the major areas where there's ice sheets. We're also seeing the sea ice changing, and NISAR is going to be tracking those changes. We're going to be able to see not only how fast the ice sheets are melting, but how fast that rate of movement is changing. So how it's accelerating and decelerating. And that's going to help us tell what's really driving those changes and how that feeds into all of the Earth system's response to global warming. We're also going to be able to look at how the forests are changing. So NISAR is going to be measuring the extent of forested areas. So we call that biomass, which is a term for, how much woody carbon, so how many trees basically are in the forest. And that is something that can influence the global response to climate change. So are the trees growing more and collecting more carbon? Are they decreasing? Are they under stress from climate change? And how is this feeding into the carbon cycle in the Earth? So those are two main ways that we're going to be looking at, or NISAR is going to be able to inform us. I didn't even mention sea level rise. Okay, yeah. So when the ice sheets melt, it's going to be increasing the volume of the ocean, influencing sea level rise. We're also going to be looking at how the coastal areas are changing and how that also influences the impacts of sea level rise. So there is the oceans increasing their volume as part of sea level rise. There's also the fact that the coastal areas themselves could be either sinking or uplifting. And so that's going to be that's something that the people who live in those areas really need to know as they look at projections of how much the seas are going to be rising in their local area over the next 10, 20, or 30 years. And NISAR, with its global coverage and high spatial resolution, is going to give people the information that they need for their local region in estimating the impact of sea level rise.
So great information in the hands of people who need it to make the future better, which is really important. All right, we got another one on YouTube from AO. Can this satellite recognize a snow avalanche or mudslide and give warning before they happen?
Yeah. So that's a really good question. I think, those types of questions are the exact types of questions that the people using NISAR data are going to be exploring after a launch. And right now, the current radar data, we might be able to get some constraints on the, what would be causing avalanches of snow, how much snow is in the mountains, say, or for mudslides. I mentioned soil moisture. If the ground is really wet, we would be able to, we want to know how wet the ground is, and that's going to influence our predictions of mudslides. But right now, a lot of the data that we have for that, it's over a fairly large region, so it's hard to use that for predictions of like one particular avalanche or one particular mudslide. With this higher spatial resolution data, how much better can we do? How much better information can we provide? These are the types of things we're going to want to be testing once NISAR launches.
Everyone's concerned with preemptively striking, so it's going to be a good precursor. Yeah. And I think this one is for you, Wendy. So we're asking, let's see, Stunblade13 on Instagram asks, how long will it be in space, and does it have the regenerative battery, or is it solar?
It runs on the solar array, but it is designed to operate. We designed it to operate at least 3 years on orbit. We expect it'll last longer, but that's what we're promising from a mission perspective. But yes, we have a battery, but it's regenerated with a solar array.
Oh, wonderful. Okay, well, that's all the time we have for questions here today. And thank you so much, not only to our mission experts, but also to each and every one of you who actually joined us here today in this very special clean room on this very special day before we send NISAR off. So let's take a little bit of a closer look here at NISAR for you all, so you can have a nice last look here. And NISAR is expected to leave JPL next month as it continues its journey to India, where it's going to be tested and integrated as well in their location. And it is going to be launching in 2024 from the Satish Dhawan Space Center in Sriharikota, India, as I mentioned, in 2024. And if you want to learn more about the mission, make sure you follow us at NASA JPL, also our sister channels at NASA Earth and at NASA Climate Change. And we've got a lot of information on NISAR and all of our Earth projects there. And just remember, at NASA Earth Science, your home is our mission. Thank you so much for watching today, and go NISAR!